Hello. Today we're going to talk about projectile motion. So first I'm going to just kind of remind you of these slides from the end of the lecture on Monday. So we talked about how perpendicular motion or horizontal motion versus vertical motion are independent of each other. So we have the example of one ball dropped down and the other ball launched to the side with some speed, and we see that they will hit the ground at the same time. So that speed in the horizontal direction does not affect the vertical motion. And projectile motion is this idea that the motion of an object when launched at an angle is going to be a parabola like this. And so here's that same, well, it's not really the same parabola, but it's a parabola. And we have this initial velocity. So the purple is our total velocity. So initially it's at this angle theta naught, and it's this velocity naught, which is what that subscript 0 means, or like how you say it. And we can see that this purple vector changes throughout the trajectory. And it is the kind of vector, if you did vector addition of the y component, which is this blue one, and the x component, which is this blue one, and the y component, which is this orange-ish one. And so let's first just look at the blue one, and we can see that it's constant through the whole trajectory. The whole time, the horizontal velocity remains the same. And this is because there's no acceleration in the horizontal direction if we're ignoring air resistance. And then in the y direction, we can watch how as it goes up, this orange vector gets smaller until it disappears. And then it switches direction. It goes from pointing up on this half to pointing down, and it gets bigger as it approaches the ground. And an important thing to note is this represents the maximum height in projectile motion, and that is when that velocity in y is 0. But velocity in x is not 0 there. So one thing to think about, for the most part with projectile motion, there is an initial velocity at a certain launch angle. So you'll be given like initial velocity 3 meters per second. It's not usually going to be 3 at an angle of 15 degrees. That will be the information you need, and then you can find the y and x components of that, and we'll do some examples of this. I also want to note a couple things. So range is a term you might hear, and range is just the horizontal distance or the distance in x. And one thing to note is that the launch angle affects the range. So if we launch at so this little blue one down here is 15 degrees, like I just said. So if we launch something at 15 degrees, it's not going that far. But for maximum launch, if we launch it at 45 degrees, it will go its farthest length possible. And then in between 45 and 15, it'll go far. And you can also see here that we get the same range for 15 degrees and for 75 degrees. It just goes a lot higher for 75 degrees than it does for 15. So those are just kind of important ideas to keep in mind. And then one more thing, these are some kind of definitions you can keep, like, hold on to. for dealing with projectile motion problems. So your acceleration in the y direction is always going to be negative g, negative 9.8 meters per second squared, and the acceleration in x is going to be 0. You can always count on those. And then the initial velocity in y will be given as the initial velocity times sine theta, and then the initial velocity in x will be times cosine theta. But we'll look at that in the examples that we're going to do. So here's the first example. In the sport of dock jumping, dogs run at full speed off the end of a dock that sits a few feet above a pool of water. The winning dog is the one that lands farthest from the end of the dock. If a dog runs at 8.5 meters per second, straight off the end of the dock, that is 0.61 meters above the water, how far will the dog go before splashing down? And one thing, maybe I'll just note now, and I'll note it again while we're doing the problem, is so they give us just this 8.5 meters per second. They don't say anything about an angle. And so that tells us that we're leaving with just horizontal motion. Like we have only horizontal velocity, not vertical when we take off. But we will look at that. Okay, first I'm going to draw the situation. So here's the dog. Here's the water. Let's see, it's 0.61 meters high. I'm going to draw a really bad drawing of a dog. There you go, there's a dog. It has this initial velocity that's only in the horizontal direction. And what we want to know is what the range is, or X position, when the dog hits the water. So let's do our knowns. One thing we can say is we're going to make this point, like right where the dog jumped off the dock, is going to be kind of our origin of our coordinate system. So that tells us that our initial position in X is 0 meters, but our initial position in Y, oh yeah, I don't want to do it like that though, actually, I'm sorry. We're going to undo. I guess we're going to redraw. So I actually want to put it at the water. You can do it either way. It's just at the water is what I did before. So I'm trying to follow that. So, okay, X initial equals 0 meters. Now, Y initial is 0.61 meters, because that's the height of the dock, and then Y final is 0 meters. But again, you could set this at the dock, and then Y final would be negative 0.61 meters. Then we have our initial velocity in X, which is 8.5 meters per second. And then let's see, I guess we can say the initial velocity in Y is 0. And then we can say acceleration in Y is negative g, and acceleration in X is 0. Lots of stuff is 0, that's good. Unknowns. So we don't know the time, but it's not asked for, so maybe we don't need it, we'll see. And we don't know that final position in X. So how these projectile motion problems work is usually what you're going to have to do is solve one problem for time. I know I just said maybe they won't require time. You're going to have to find time. One variable for time and the other variable for some other thing. So in this case, we're going to use Y to solve for the time, and then we'll use X, and then we'll use that time to find the final position in X. So let's take a look at that. We have the final. Also, apologies if you hear background noise. It's trash today and the recycling truck is coming. So, but I'm just gonna write all the equations in Y. And we'll go through those with what we have. Y initial plus V initial Y delta T plus 1/2 A delta T squared. And then we have V final squared equals V initial squared plus 2A delta Y. Okay, so let's go through what we know and don't know. So we don't know the final velocity. We know the initial velocity and remember this is in Y. In Y. And we know the acceleration in Y and we don't know the time. So that one has two unknowns. We're probably not going to use it. And then we know the final and initial Y. We know the initial velocity in Y is 0. We don't know the time. We know the acceleration and there's the time again. So that one looks okay. There's only one thing we don't know. And then this one, we don't know the final velocity in Y. We know the initial. We know the acceleration and we know the displacement, but time's not in there. So if getting the final velocity doesn't really help us. So we're going to use this equation. Let's see, Y final equals Y initial plus V initial Y delta T plus 1/2 acceleration delta T squared. So let's take a look at this. First of all, our initial velocity in Y is 0. And our final position in Y is 0. So we can cancel those ones out and say 0 equals Y initial plus 1/2 the acceleration times the time interval squared. And then we can just solve for the time interval. So that's going to look like subtracting Y initial on both sides. Let's do that. Negative Y initial equals 1/2 acceleration delta T squared. And then we're going to divide 1/2 the acceleration on both sides. That gives us negative Y initial 1/2 acceleration equals delta T squared. And then we're just going to take the square root of both sides. And that will give us negative Y initial over 1/2 acceleration equals the time interval. And then I'm gonna plug in partially. So I'm gonna say negative G so that we can see that, oh, our negative sign cancels out, which is good because you can't take the square root of a negative, or you can, but it's an imaginary number. So now we'll plug in our numbers. So this initial height in Y is 0.61 meters. Then we got 1/2, and then it's 9.8 meters per second squared. So this time is 0.35 seconds. So that's the time that from jumping off the dock until the dog lands in the water. So now we can use that time to find the range or the final position in X. And because there's no acceleration in X, we can just use the that first equation that we don't use that much because it's for when you don't have acceleration. But let's double check that we're good to use it. So let's see. We want this. We have that. We have that, and we just got time. Cool. We can use this equation. And we don't even have to rearrange it. And I can also say, oh, look, that's 0. So the final position is the initial the velocity times the time interval. So the velocity is that 8.5 meters per second, and then the time interval is 0.35 seconds. And this gives us 2.975, which probably the I don't know, judges of the competition would pay attention to that precision, but we know that we need to round. So we're just going to round up to 3 meters. And so that is how far from the dog lands. I'm just going to go back over what we did really quickly. So we drew a beautiful picture of the situation, and then we wrote our knowns and unknowns. And then I told you that for projectile motion, usually you're going to have to find the time with one variable and then whatever else you're looking for with the other one. So that's what we did. We found the time with y because we had enough information to do that. And then we used that time to find the range in x. Next one. These next two are both soccer. I don't know why they were just, I don't know, maybe that's just popular for a parabola. Makes sense. Okay. In a soccer free kick, a player kicks a stationary ball toward the goal that is 18 meters away. He kicks the ball at an angle of 22 degrees from the horizontal at a speed of 23 meters per second. How long does the ball take to reach the goal, and how far off the ground is the ball when it reaches the goal? Okay, so we're going to start with a drawing again. So we have our player, and there's the ball, and it's going to go at an angle, theta. And then here we have a net, and this distance is 18 meters, yeah. Okay. And then I also want to, since this time the velocity actually has a launch angle, I want to kind of imagine like we're zooming in on that so we can get a better look. So V initial, and then we have this angle theta. And so we have a y component, or sorry, I keep doing that, x component and a y component. B initial y, and this should be B initial x. And looking at this, we see that the x component is adjacent to the angle. So the initial x is going to be the initial velocity times cosine of theta. And then that means that y is opposite. So the initial y equals the initial sine of theta. Okay, now that we've laid that out, let's do our knowns and unknowns. So let's see. Well, one thing we can say is this is where our origin is. So that tells us that our initial y is 0 and our initial x is also 0. We also know what our final x is because they told us that the goal is 18 meters away, and that's we're looking for how long it takes to get to that position. We have the initial velocity of 23 meters per second at an angle of 22 degrees. And then let's see. The acceleration is the other thing. So acceleration in y is negative g, and acceleration in x is 0 meters per second squared. Okay, now our unknowns. We don't know how long it takes to get that travel that 18 meters. And then we also don't know what the final y value is, because this says how far off the ground is the ball when it reaches the goal. So that tells us that it's probably not on the ground. So now, again, we're going to have to use one equation to get time and another equation to get the other variable we're looking for. And so let's look at this equation in x, because again, the acceleration is 0. And then we'll look at this equation in y, the initial y, delta t plus 1/2 ay delta t squared. Okay. So we want both this and that. let's see. We know this, and that. Okay, so we can solve for time from that equation. And we know this, we don't know time. We know acceleration, we don't know time. So we will solve for time in our x equation and then put that time into our y equation. So let's take this x equation. Yeah, x final equals x initial plus velocity in x times the time interval. And we want to find the time interval. So first thing is the initial position is 0. X final equals v delta b. And then we're going to divide the velocity on both sides. So that's going to give us the final position divided by this initial velocity in x, which we found before that that's going to be the initial velocity we're given times cosine theta. Cosine theta. So and that is the time interval. And so we can plug in our numbers, 18 meters and divided by 23 meters per second times cosine of 22 degrees. Yes. And this gives us a time interval of 0.84 seconds. So cool, we can take that time interval and plug it into our equation in y and then update this. We know the time now, so the only thing we're missing is that final position. I'm going to use a different color. So the final position equals the initial position plus initial velocity in y times the time interval plus 1/2 acceleration times the time interval squared. Okay, so one thing we can say is that the initial position in y is 0. And then the rest, it's already solved for y final, so we can just plug stuff in. I'm going to write this as the initial sine theta, because that's the initial velocity in y. And then I'm also going to plug in negative g here, 1/2 g delta t squared. Now we'll plug in our numbers. So this one is 23 meters per second, sine of 22 degrees times 0.84 seconds minus 1/2 times 9.8 meters per second squared times 0.84 seconds, whole thing squared. This gives us a height of 3.78 meters. And so that is our height once the ball reaches the goal, but this isn't listed in the problem, but I was wondering, does that mean the soccer player made the goal or not? And so I looked up the height of a goal. And so the height of a goal is 2.44 meters. That means that this ball is kicked too high and he misses. Bummer. Okay. Last example, it's a little longer, it has more parts. It is soccer again, though. A soccer player kicks a ball at an angle of 36 degrees from the horizontal with an initial speed of 15.5 meters per second. Assuming that the ball moves in a vertical plane, find the time at which the ball reaches the highest point of its trajectory, its maximum height, its time of flight and range, and its velocity when it strikes the ground. So that's a lot of things. And we'll lay that out. First, though, let's draw the situation. Player, ball, initial velocity, angle. And we will do this again. So here's our initial velocity and the angle theta. And then we have x initial and y initial. And the initial x is going to be v initial cosine of theta again. And v initial y is going to be v initial sine of theta. And this is what it will be unless the angle you're given is weird and it's from the vertical instead of the horizontal. This is what you'll do for projectile motion. But it's not always gonna be this way when we have things at an angle. It's just specifically for projectile motion, it will. Okay, so then our knowns. Again, we can say this initial position is our origin. So initial y position is 0, initial x position is 0, and the initial velocity is 15.5 meters per second. Angle is 36 degrees. Acceleration in y is negative g. Acceleration in x is 0. And we'll write unknowns now. There might be more things, but this is kind of broken up into different parts of the motion. So might need to spread things out a little bit. So it asks us for the maximum height, the time to that maximum height, asks for the total time, the range, and the final velocity. Yeah, final velocity. I was going to say in y, but I think it's just the final velocity. So now let's draw the trajectory because we're asked about things from like different points in the trajectory. So there's the ground. So I'm going to call this point 0, this point 1, and this point 2. So this is where we start. We have our initial velocity and our angle. And this is where we get that maximum height. But we can write down some things about this point in addition. So, or really just like one more thing. Remember that the peak of the trajectory, the velocity in y is 0 because this is that turnaround point where it's going to go from velocity pointing up to velocity pointing down. So velocity 1 in y is 0 here. And then we know acceleration is in y is negative g. And the x hasn't changed because there's no acceleration in x. And then the only other thing too at position 2 is that y final-ish for that is 0 because it's back on the ground. So let's see what we can do to answer the first question, which is t, or time to maximum height. So that's going to be this one position on the trajectory. So let's see. And again, highest point means velocity in y equals 0. So let's see, we want the time. Let's take a look at this equation, see if it has everything we need. So v final equals v initial times acceleration, or plus acceleration times the time interval. So we know this is 0, we know what that is, we know what that is, and we want this. Cool. We can use that equation then. Might be able to use a different equation too, but either way. So let's write our equation. V final equals V initial plus A delta T, and then, oops, V final is 0. So 0 equals V initial plus A delta T, and then we're going to subtract the initial velocity on both sides, and that's going to give us negative V initial equals A delta T, and then we're going to divide both the acceleration on both sides. Negative V initial over acceleration in y is delta T, and so this is V initial in y also, so that is negative v initial sine theta, and then acceleration is negative g. So those negative signs are going to cancel, and we can plug in our numbers. Let's see. So this one is 15.5 meters per second, sine of 36 degrees, divided by 9.8 meters per second squared. So that's going to give us a time to the maximum height, T max, is 0.93 seconds. Okay, that's the time to the maximum height. And then they ask for the maximum height. So let's do that part B. Maximum height. So that is just going to be y2, like we described in the trajectory, which is when the time interval equals that 0.93 seconds. So now we can probably use that time to find the position. And so let's look at the next equation, which is the long kinematics equation. So y final equals y initial plus v initial in y delta t plus 1/2 acceleration in y delta t squared. Okay, and let's make sure we can use this. We want to know what y final is. We know what initial is, it's 0. We know initial velocity, we just found the time interval, and we know acceleration in the time interval. Cool, awesome, we can use that. So y final equals y initial plus b initial y delta t plus 1/2 ay delta t squared, and then y initial is 0. We decided. Okay, y final. And then we can plug in what these equal before we plug in the numbers. So b initial y is the initial sine of theta, and then we multiply by the time interval. And then I'm going to pull that negative out here because acceleration in y is negative g. That's a d squared. Now we can plug in numbers. 15.5 meters per second, sine of 36 degrees, times the 0.93 seconds, minus 1/2 times 9.8 meters per second squared, times 0.93 seconds, whole thing squared. So that gives us a maximum height of 4.2 meters. Y max. There we go. And then C asks for the time of flight and the range. Time of flight and range. Okay, so let's look at a couple of equations. So we'll look at the equation in X for constant velocity, because we have on constant velocity. And then we'll look at the long kinematics equation again. Plus v initial y delta t plus 1/2 acceleration in y delta t squared. Okay. Let's see. So we want this final position in X. We know our initial, we said it's 0. We know our velocity, but we don't know the time. And for y, one thing we can say is that y final in this case is when it hits the ground again. So it's 0 again. So we know that. We know initial is also 0. We know the initial velocity. We don't know the time. We know the acceleration and don't know the time. So it looks like we need to solve for the time first and then plug that into this other equation. So let's do that. Let's see. Y final equals y initial plus v initial y delta t plus 1/2 acceleration in y delta t squared. So first off, both of these positions are 0. So we get 0 equals v initial y delta t plus 1/2 acceleration in y delta t squared. And then one thing we can do is just divide everything by delta t, which is going to cancel out that one and cancel out the square on that one. So that's just because both terms are multiplied by delta t and the whole thing is equal to 0. So we can just make our lives easier. So this gives us 0 equals v initial y plus 1/2 acceleration in y times the time interval, not squared, just the time interval. And then we can solve that. So we'll subtract the initial y from both sides, which gives us negative v initial y equals 1/2 acceleration in y times the time interval. And then we're going to divide 1/2 acceleration in y on both sides. So that gives us negative v initial y over 1/2 acceleration in y equals the time interval. And then let's write these out. So negative v initial times sine of theta for v initial in y. And then negative 1/2 g, so that our negative signs cancel. And we get, we'll plug the numbers now, 15.5 meters per second, sine of 36 degrees, divided by 1/2 times 9.8 meters per second squared. So this gives us a time of 1.86 seconds. So now, well, that did answer part of the question. It did ask for the time. But now we want to use that to find the range or the final position in x plus b x delta t. And now we have everything we need to solve that, and we don't even have to rearrange this equation, which I appreciate. So 0 for that guy. So we have x final equals velocity in x times the time interval. And then velocity in x is the initial velocity times cosine of theta times the time interval. And so now we'll just plug those in, 15.5 meters per second, cosine of 36 degrees times 1.86 seconds. And this gives us a final position of 23 meters. So that's the range. And remember, the range is just how far it travels in x. That's C. And then part D asks us for the final velocity. I do want to point something out for you though. So to make it faster the next time you do it, oops. If you look, this maximum height is half of the time to maximum height is half of the total time. So that is not an accident. That's how it works, because we can say that the time to get halfway through the trajectory, 1/2 time, is equal to the time going from the peak to the end point. So in the future, if you find the time of the max height, you can just multiply that by 2, as long as what you're looking for is the time for it to like reach the same height as it was initially. Sometimes some object might be like launched from a cliff, and so the y position is going to go negative compared to, or it's going to go below where it initially was, but not when we're starting and ending on the ground. You're good there. Okay, so now last part is D, and this one asks for the final velocity. So in x, because there is no acceleration, the final equals the initial, equals the initial cosine of theta. Easy peasy there. And then v final in y is equal to the v initial in y plus the acceleration times the time interval, acceleration in y. And this is the time interval, so like the total time here. because we're looking at the final velocity. So that's one v initial sine theta plus acceleration in y times the time interval. And now we can plug this in. And we get 15.5 meters per second, sine of 36 degrees, minus 9.8 meters per second squared, times the time interval of 1.86 seconds. And this gives us a final velocity in y of negative 9.12 meters per second. Final velocity in y. And then that makes sense that it's negative because it passed the peak already, which means the velocity is going down. And then we'll just plug, because I didn't plug in the x1 ahead of time for myself, so we'll just plug in those numbers in here. Let's go, because the total final velocity is the final velocity in x squared plus the final velocity in y squared. So that's going to be the square root of that 15.5 meters per second times cosine of 36 degrees squared plus negative 9.12 meters per second squared. And that whole thing is square rooted. And so we get 15.5 meters per second, but now we're going down. And so you say, that's the same as launch speed. Yes, exactly, because the behavior, or like the speed, is going to be the same at any of like the same position in y. So for example, if we were right here, that's the same height in y, so this velocity is going to be this way. That velocity is going to be that way, but their magnitudes are the same. It just happens that for y, it's going from positive to negative. Okay. So yeah, that last problem was a long one. But it also, part of why I wanted to do it, because it kind of shows you most of the things you're asked for in projectile motion. Okay, have a great day.